Yeah. So we completed questions on limits and continuity from NEST, and we will today solve some of the previous year's questions based on differentiation or derivatives. Now you'll find a lot of common questions like differentiable, continuous, and all that stuff. Let us start with our first question of the day. This question is from NEST 2007. Consider the polynomial function f of x equal to x cubed minus 9x squared plus 23x minus 15. X belongs to negative infinity to infinity. Option A, f of x assumes every real value at least once. Option B, mod of f of x is differentiable everywhere. Option C, f of x has a local minimum in the interval 3 to 5, closed interval 3 to 5. Option D, for x less than 0, the curve y equal to f of x lies entirely in the third quadrant of the xy plane. Okay, now this is actually a multiple select question, so there may be more than one option correct. Okay, alright, so we will start by writing down the given function, which is x cubed minus 9x squared plus 23x minus 15. Okay, now first of all note that coefficient of x cubed is positive, right? Coefficient of x cubed is positive, and therefore I can say that limit of f of x as x tends to infinity is infinity. Correct? So as x gets larger and larger, x cube is going to dominate all the lower power terms no matter how large their coefficients are. So this is going to be infinity, and if x tends to negative infinity, then also we will not get the same result, but we will get numbers which are very large in magnitude but negative in sign. Okay, so hope you understood that. Limit of f of x as x tends to infinity is infinity, and limit of f of x as x tends to negative infinity is negative. Okay, now we know that f of x is a polynomial, right? F of x is what? Polynomial. And for polynomials, we know the characteristic that they are continuous and differentiable everywhere. So we can say therefore by intermediate value theorem, okay, by intermediate value theorem, range of f of x is negative infinity to positive infinity. Raise your hands if you have understood this particular argument. Okay, so option A is right. Okay, option A is right. Now to talk about option B, C and D, okay, talk about options B, C and D, let us take a look at the functions coefficients. Let us take a look at the functions coefficients. Okay, now what is the sum of coefficients? Okay, have you looked at it? Sum of coefficients, let us see. X cube's coefficient is 1, x squared's coefficient is negative 9, x's coefficient is 23, and the constant term is negative 15. Okay, 23 plus 1 is 24, 9 plus 15 is also 24, 24 minus 24 is 0. Now what does this imply? This implies that f of 1 is 0, and therefore x minus 1 is a factor, right? X minus 1 is a factor. Now to find the other two factors, okay, we don't know whether they are real or they are complex conjugates of each other, the roots. Okay, one of the roots is definitely 1, so we can divide this polynomial. Okay, we can divide this polynomial by x minus 1. Let us see how, well, rather what we get there. Okay, see, we are bound to get 0 remainder, right? We are bound to get 0 remainder, but we would like to see the quotient. Okay, first we will have x squared, so it will be x cube minus x squared. With that negative sign, this will go and this will become negative 8x squared plus 23x minus 15 will get carried forward. Okay, then what are we going to get? Minus 8 should be there, minus 8x, right? So it will be negative 8x squared plus 8x, correct? Again subtract, x squared goes 23 minus 8 will be 15x minus 15. So all we have to do is we have to just add 15 here and that will make it 0. Okay, now after successfully factorizing the given polynomial, let us check whether we can factorize the coefficient of the quotient, sorry, not the coefficient, the quotient, which is x squared minus 8x plus 15, correct? And it's not very difficult to see that negative 8 can be written into, well, split into negative 5 and negative 3, and so is this. And that's exactly what we need when we look for factors, correct? So we can write f of x as x minus 1 into x minus 3 into x minus 5. Okay, is it clear? Yes. Therefore f of 1 is 0, already known, f of 3 is 0, and f of 5 is also 0. Did you understand this? Yes. Okay, so our polynomial has got 3 real roots. Okay, now look, well, had we known that earlier, we would have directly checked for that, right? We would have checked for f of 3 and f of 5, but of course in the exam we will not be knowing that, right, unless we do it manually. Okay, so we have done that. F of 1 is 0, f of 3 is 0, and f of 5 is equal to 0. Okay, now let us come to this option D. Okay, option D says for every negative x, the curve lies in the third quadrant. Is it true? Let us verify. Okay, look now. Suppose this is our x-axis, okay, and let's say this is y-axis. Okay, 0 is here, 1 is here, 3 is here, and 5 is here. Oh, well, forget about the scale. Now look, when x is greater than 5, okay, when x is greater than 5, then what will be the function's value? Will be positive, we know that. When x is in between 3 and 5, okay, x is in between 3 and 5, what will happen? These two terms will be positive, but x minus 5 will be negative, so here the curve will be negative. Okay, and when it comes to numbers between 1 and 3, then these two factors will give us negative, and x minus 1 will be positive, so negative into positive, so again that would be positive. So to the left of 1 we are getting all negative values, right? To the left of 1 we are getting all negative values. If you understand this, because we know the factors, then you know that the shape of the curve, roughly how it looks, right? It's going to be something like this, and here it will go like this. Okay, and where will it intersect the y-axis? F of 0 will be negative 15, so wherever that curve is going to meet the y-axis, that point will be negative 15. So is option D correct? For x less than 0, the curve lies entirely in the third quadrant. Yes, it is, because after it crosses negative 15, the whole of the curve is going to be in the third quadrant. Okay, so option D is also right. Okay, option D is also right. Okay, option D is also right. Now, based on this particular picture that we have sketched, okay, let us decide which one of the options B and C is true, or both are true. Okay, or both are true. And just to support our arguments, okay, just to support rather the curve that we have drawn, the shape of the curve that we have drawn, what I think we should do is, okay, we should go for f dash of x. Okay, we should go for f dash of x. I'll tell you why, but first let us find the derivative of f. Okay, first of all let us find the derivative of f. Okay, what would it be? F dash of x would be 3x squared minus 18x plus 23. Okay, now what is f dash of 1? It would be 3 minus 18 plus 23. Now we don't care whether what value it is, but we know for sure that it is positive. Okay, so the function is increasing at x equal to 1, we know that. Okay, now let us calculate f dash of 3. Let us calculate f dash of 3. What is f dash of 3? 3 into 9, so that is 27 minus 54 plus 23. Okay, 27 minus 54 plus 23. Now that is definitely less than 0, so the function's graph is going down and decreasing. Okay, and what is happening at 5? What is happening at 5? It would be 3 into 20, so that is 75 minus 90 plus 23. Okay, 75 plus 15 is 90, so this will definitely be positive, which means the function's graph is again increasing there. Okay, which now confirms that between 3 and 5 it has a local minimum, so C is right. Okay, between 3 and 5, well, because the sign of the function changes between 3, well, at 3 and at 5, so between 3 and 5 we must have a local minimum. Is it clear? Where is that located? We don't care. Rather, that's not of any concern to us. So option C is also right. Now what needs to be decided is whether option B is right or wrong. Okay, here they are saying mod of f of x is differentiable. Now look here, the graph of mod x will actually be the mirror image of the graph of f of x when f of x is negative. Correct? So if I were to sketch the graph of mod x, okay, I will have a sharp corner here. Okay, I will have a sharp corner here. Okay, so because of these corners, okay, at x equal to 1, x equal to 3 and 5, box f of, sorry, not box, mod f of x has corners like mod. Okay, now because of that it won't be differentiable. Okay, so it's not differentiable here, so B is not right. Have you understood our argument, what we have said there? At how many points is our function not differentiable? At 3 points. At x equal to 1 it is not differentiable, at x equal to 3 also it is not differentiable, and at x equal to 5 also it is not differentiable. Is it clear? Yes? Got it? Now let us verify this graphically. Okay, let us verify this graphically. What was it? X cubed minus 9x squared plus 23x minus 15. 1, okay, that's true, that's true, that's true. Okay, 135, that's perfect. And now let us go for mod of f of x. Oh, sorry, mod of this function. And as you can see, except that McDonald's thing, okay, like the blue only has different shape than the red one in whenever the blue is, the red is below the x-axis. Okay? Okay, now let's see if we can find the derivative of this function mod 1. Okay, the derivative here. Okay, now see, it is showing exactly vertical, so from this it's not going anywhere. Okay, it's not going anywhere. Here from the left, if you see, the derivative is -4, but from the right you see the derivative is positive 4. Okay, and see, this is a vertical line that the software has drawn. Okay, but that is not right. Okay, there is a discontinuity that our function is going to, it's not capturing it. Okay, well, maybe right here it has captured it. Okay, the function is discontinuous there, and therefore it is not differentiable, the original function. Got it? Yes? Okay, question 1 done. Let us go to question number 2. Question number 2. This is from NEST 2008. Okay. A real function f of x is given by f of x equals alpha x squared plus beta x for x less than 0, alpha x cubed plus beta x squared plus 5 sin x for x greater than or equal to 0. If f of x is twice differentiable, then alpha 1 beta 0, alpha 1 beta 5, alpha beta both 1, alpha beta both 5. Okay. Now look, these functions that you see, what are these? These are polynomials. Okay, and plus this second function has sin x there, but all of them are continuous and differentiable everywhere. Correct? These are continuous and differentiable everywhere, no matter what values alpha beta have. Which means we need to only look at the point 0 where the function's definition changes. Right? Definition of the function changes, so that is the only point of concern now. Okay, they are saying that it is twice differentiable, so let us go for f dash of x now. Okay, alpha x squared plus beta x, so that would be 2 alpha x plus beta. Okay, 2 alpha x plus beta for x less than 0, and 3 alpha x squared plus 2 beta x plus 5 cos x for x greater than or equal to 0. Now let us see if this function is continuous at 0. Okay, what are we getting? When x is 0, we get this as beta, and when x is 0, we get this as 5. So beta is 5. Okay, beta is 5, so option A gone, option C gone. Now let us calculate the second derivative. It's 2 alpha there, and here it is how much? 6 alpha x plus 2 beta minus 5 sin x. Okay, it is also differentiable there, twice differentiable there. Okay, it is twice differentiable there, so here we are getting 2 alpha at 0, and here what are we going to get? Here we are going to get 2 beta, and because it is twice differentiable, okay, what should we must have now? We must have 2 alpha equal to 2 beta, which implies alpha to be 5. Okay, which implies alpha to be 5, so correct option is D. Alpha and beta both are equal to 5. Is it clear? Yes? Okay.
Yes, sir.
Yeah, Aishwarya, good afternoon. Why were you late today?
So there were like a few things going on at home.
Okay. Fine. We have actually solved a problem which took us quite long because it was a multiple select question. So you go through it, and if you have any difficulty, you ask me later. Okay. Question 2 was pretty easy. Now we are on to question number 3. Okay, we are on to question number 3. This question came in 2008, same year as the previous one. Let f of x be the minimum of x comma x minus 2 squared for x greater than or equal to 0. Option A, f of x is continuous on the open interval 0 to infinity. Option B, f of x is differentiable on the open interval 3 to infinity. Option C, f of x is differentiable in the closed interval 2 to 3. And option D, f dash of x exists and is continuous on the open interval 1 to 4. Okay, now look here. The domain of our function according to the problem is closed interval 0 to infinity. Okay, and we also know that the graph of y equal to x will be making an angle of 45 degrees, but I will not draw it in the third quadrant because it is not required. Okay, so this is going to be our graph of the line y equal to x. Let me draw it in red color. Okay, fine. Now let us go for the parabola. Okay, let us go for the parabola, and to find the points of intersection, okay, we need to solve the equation simultaneously, but if you can find the points by observation, good. If you don't, it's okay. Look, x squared looks like this, isn't it? X squared looks like this. So x minus 2 squared will have its minimum at here, at 2. Okay, it will have its minimum somewhere here. Okay, so it's going to look like this. Okay, so somewhere there they will meet. So what do you realize now? In between this point and this point, okay, it will be y equal to x. Okay, then in between this point and this point, it would be x minus 2 bracket squared. Okay, x minus 2 bracket squared, and after that, beyond that, it will all again come to y equal to x. Okay, so can we find the points of intersection of y equal to x and y equal to x minus 2 squared? Yes, that's pretty easy actually. Okay, we need to solve the two equations simultaneously. X squared minus 4x plus 4, therefore x squared minus 5x plus 4. The split is simple now, negative 4 and negative 1. Okay, negative 4 and negative 1, that's pretty simple. So clearly this point is 1 and this point is 4, and we can also come back to the definition and check whether they indeed intersect. For y equal to x, 1 gives 1. Y equal to x minus 2 squared, again 1 is going to give 1. Same thing with 4 and 4 minus 2, 2 squared 4. Okay, so that's 1 and that's 4. So this definition is for x less than or equal to 1. This definition is for x in between 1 and 4, and this definition is for x greater than or equal to 4. So it is definitely continuous on the open interval, correct? So A is correct. Okay, A is correct. Now let us go to B. F of x is differentiable on the open interval 3 to infinity. Now why is that not true? That is not true because, look, suppose we go for derivative. Okay, suppose we go for derivative, it would be 1, 2 into x minus 2, and then again 1. Okay, now at 3 what is happening? At 4, what is the left hand derivative? At 4, the left hand derivative will be 2 into 4 minus 2, that is 4. And what is the right hand derivative? It is 1 actually. Okay, it is 1. So again, this is for x less than or equal to 1, 1 less than x less than 4, and this is for x greater than or equal to 4. So clearly at 4 it is not differentiable, it is a corner there. So is it differentiable on the open interval 3 to infinity? No, as 4 belongs to this interval. Okay, C. F of x is differentiable on the closed interval 2, 3? Yes, because that interval is in between 1 and 4. F dash of x exists and is continuous on the open interval 1 to 4. Look, between between 1 and 4, no matter what point you take, all of those points on the graph will be on the parabola, because 1 and 4 happen to be the points of intersection, and this is an open interval. If you see, okay, what interval is that? It is an open interval, so you take any point, no matter how close you are to 1, but you should be right of 1, and same thing with 4, but to the left of 4. Is it continuous? It's continuous. Does it exist? Yes, it does exist. So except B, all options are correct. Let's go through them again. F of x is continuous on the open interval 0 to infinity. Well, no question. Option D, or like, let's go to option B now. F of x is differentiable on open interval 3 infinity. No, because 4 belongs to that interval. It is differential in the closed interval. Yes. 2 is greater than 1, 3 is less than 4. And D, f dash of x exists and is continuous on the open interval 1 to 4. That is also true, because in 1 to 4, what is the definition of the function? X minus 2 bracket squared. Have you understood this?
Yes, sir.
Yes. Okay. If you have not understood it, please ask me. Okay, please ask me. Okay, question number 4. Another simple question. This is from 2009. Consider the function f from R to R defined by f of x equal to e to the power 3x for x less than or equal to 0, 3 by 2 e to the power 2x minus 1 upon 2 for x greater than 0, then f of x is not continuous at 0, continuous at 0 but not differentiable there, differentiable but not twice differentiable there, twice differentiable at 0. Pretty straightforward, because the exponential function is there and you're subtracting a constant from that, so continuity and differentiability individually will not be affected, or even twice differentiability. Okay, let us go for continuity now. Okay, what is LHL at 0? LHL at 0, LHL at 0 will be e raised to 0, that is 1. What is the right hand limit? 3 by 2 into e raised to 0 minus 1 by 2, 3 by 2 minus 1 by 2, 2 by 2, 1. So that is continuous. Okay, that makes it continuous. So option A gone. Okay, now let's take the left hand derivative. First left hand derivative. Derivative of e raised to 3x is 3 into e raised to 3x. So that is 3. First right hand derivative, what would it be? 3 by 2 into, okay, 3 by 2 into derivative of e raised to 2x is e raised to 2x into 2, but again at 0 we are evaluating it. This is 3, so differentiable. Okay, so option B is also not right. Now we need to find the second derivative, and we need to see that. Okay, second derivative. E raised to 3x is first derivative is 3 e raised to 3x, so second derivative will be 9 e raised to 3x, but we are substituting x as 0, so this is 9. And what is the second order right hand derivative? Okay, so the first derivative was okay, let me write it here. 3 by 2 into 2 into e raised to 2x, right? That was the first derivative, or 3 e raised to 2x. So the second derivative will be 6 into e raised to 2x at 0, so that would be 6, and they are not equal. They are not equal. So is it twice differentiable? No, it is not twice differentiable, so correct option is C. Yes, understood? That was a fairly simple question, right? Maybe a state level
Yes, sir.
CET question. Okay, cool. Yes, this one is also from 2009, and this is actually interesting. I found this a bit more interesting. Consider the function. Okay, wait. What was the number? Fifth one. Fifth MCQ of the day. Consider the function f from R to R, f of x equal to x plus sin x, x belongs to R. Option A. The function is strictly increasing at every point on R except at x equal to an odd multiple of pi, where the derivative of f is 0 and where function f is not strictly increasing. Option B, the function is bounded in every bounded interval but unbounded on the whole real line. The graph of the function y equal to f of x lies in the first and third quadrants only. D, the graph of the function y equal to f of x cuts the line y equal to x at infinitely many points. Okay, from 2009 this question is there, and this is a multiple select question, so more than one option could be correct. Okay, so obviously first let us write down the domain, the codomain and the definitions. Okay, look, I know that sine of x will always be between -1 and +1, correct? Sine of x will always be between -1 and +1, and therefore I can say that x minus 1 will always be less than or equal to x plus sine x, and x plus sine x in turn will be less than or equal to x plus 1. Have you got this? Got it? Hope you understood
Yes,
that.
sir.
Yes. Okay. Now look, what are y equal to x minus 1 and y equal to x plus 1? They are two parallel lines. Okay, they are two parallel lines, correct? So our graph is sandwiched between the two. Therefore our graph is sandwiched between the two. Now this will help us in recognizing the validity of option B. Okay, I'll come to that later, but first let us look for option D. Okay, option D. Now look, whenever sin x is 0, okay, when sin x is 0, I can say that f of x is equal to x. Yes, and this is true for all x which are integral multiples of pi. So the graph is going to cut the line y equal to x at infinitely many points. We actually know them, where x is n pi and y will also be n pi. So option D is correct. Okay, option D is correct. Okay, fine. Now what are we going to do? Let's come to option A now. The function is strictly increasing. The function is strictly increasing. Is it true? What is the derivative of the function? The derivative of the function is 1 plus cos x, correct? Because the function itself is x plus sin x. Okay, now if you want this to be greater than 0, because we want it to be strictly increasing, not just increasing. Strictly means equal to 0 is not allowed. Okay, if you want it to be that, then what should we have? We have cos x greater than -1, correct? Now if you want cos x to be not to be equal to its minimum value, which happens at pi, 3 pi, 5 pi, 7 pi, and that, so x can't be an odd multiple of pi. Okay, x cannot be an odd multiple of pi. Now let us read option A. They say function is strictly increasing at every point in R except at x equal to an odd multiple of pi. That, at least that part is true, where the function's derivative is 0, true, and where the function is not strictly increasing. Yes, that's true, because the derivative is 0 tells us that the function momentarily becomes flat there. Okay, like an inflection point. Okay, so option A is option A correct? Yes, option A is correct. Okay, option A is correct. Okay, now let us come to B and let's make use of the text that we have written in the blue color. The function is bounded in every bounded interval but unbounded on the whole real line. That's true. Okay, that is true. Now how are we going to justify that? Okay, so because of this, okay, because of this, I can say that given an interval AB, okay, given an interval AB, what can we say given an interval AB? Okay, the value of the function will never exceed b plus 1 and will never fall uh, below a minus 1. Raise your hands if you have understood this. Right, so exactly, so is it true that it is bounded on every interval? Yes, it's bounded in every interval. But is it unbounded on the whole real line? That means, can we come up with a number? Can we come up with a number? All values of f of x are less than that? No. As range of f of x, or as range of x is negative infinity to positive infinity, range of x plus sine x is also negative infinity to positive infinity. Right? So, is it true that it is unbounded? Yes. Therefore, unbounded on R. That is, no real number m belonging to R exists such that mod of f of x is less than m for all x. Okay, no such R exists. So B is true. B is true. Now what about C? C says the graph of the function lies in the first and the third quadrants only. Now this is something that we need to worth. Take a look. Okay. The graph of y equal to f of x lies in the first and third quadrants only. Okay, look. See, this is y equal to 1. We can say this is y equal to 1. And this is y equal to negative 1. Okay. And suppose let us say this is pi by 2. And let us say this is negative pi by 2. Okay. Now look. For all x, okay, for all x in the interval 0 to pi by 2, okay, in the interval 0 to pi by 2, x is positive and sin x is also positive. Correct? For all values of x in the interval 0 to pi by 2, x is positive and sin x is also positive. Therefore, x plus sin x will automatically become positive. Okay, so both the graphs of y equal to x, okay, the graphs of y equal to x and y equal to sin x, okay, they are positive, and from now on there is no looking back because x is going to dominate, right? So I can say if x is greater than pi by 2, which is eventually greater than 1, x plus sin x will always be greater than 1. Okay, or you can even come up with a more or a tighter bound, but that's not it. So we've got it. Okay, so if you follow this and if you use the fact that x and sin x are odd, Okay, f of negative x is negative f of x, and therefore it lies entirely in the first and the third quadrants. Okay, understood. So all options are correct. For question 5, all options A, B, C and D are correct. Any doubt? Shall I explain it again?
No doubt, sir.
No? Let's check it here. Let's check it here. First, the two lines x minus 1, x plus 1. Our graph will be sandwiched between the two. That's true, and you can see that it's clearly in the third quadrant and first. Lastly, let's go for y equal to x. It cuts this line at infinitely many points. Now let us take the derivative and see whether it is at what points. Does it ever become negative? It doesn't ever become negative. Where does it become 0? It becomes 0 at all odd multiples of pi. Our answer is correct. Okay, our answer is correct. Okay, question 5 done. Let us go to question 6. This is from 2011. Next, simple question. Which of the following functions is differentiable everywhere? Okay, now for our convenience, let us choose a at 0. Okay, let us choose a at 0. So option A becomes mod x upon x. Right, option A becomes mod x upon x. So we know what this function is. This function is not defined at 0. Now everywhere, I understand by everywhere we mean for all real numbers. Okay, so not defined at 0, so no question of that being differentiable. Okay, so well, in everywhere I mean for all x in the set of real numbers. Okay, let's go to B. It is x into mod x, right? B is x into mod x. What is C? X plus mod x. Now look, x plus mod x is not differentiable at 0, so C is also not right. Okay, so A gone, C gone. Let's come to D. I know B is right, but I just want to see whether x raised to mod of x raised to 1 upon 3, rather mod x raised to 1 upon 3 is right. Now see, even this can't be differentiable because inner function is mod x, so it is not, well, it is bound to be not differentiable at 0. But let's dig deeper. Okay, let's consider x raised to 1 upon 3, and try to find its derivative. 1 upon 3 into x raised to negative 2 by 3. Right there you understood that it's in the denominator. X is in the denominator. Okay, x is in the denominator. Okay, not square root but cube root. Right, so at 0 it won't be differentiable. So which option is correct? B is right. And we know how that behaves, right? Option B. It will be y equal to x squared in the first quadrant, and it will be y equal to negative x squared in the third quadrant, pretty much like y equal to x cube. Okay, so which option is correct? C gone, B is right, D is also not. Now always keep this habit of checking your answer whenever possible. Okay, now let us come to the grapher and see. Okay, first let's go for mod x by x. It's not different, it's discontinuous at 0, so no question of being differentiable. X into mod x, that's true, it is differentiable there, because the way closer we go to 0, the curve becomes flatter and flatter, right? Okay, what other options did we have? X plus mod x, no, that's that red one, it is 0 for negative values, and mod x raised to 1 upon 3. Okay, This is the derivative. Okay, this is the function, and you can see that it is forming. Well, we gave it a specific name that, but in this particular situation, okay, we call it a cusp. Okay, this is CUSP, cusp at 0. Okay, that's actually a cusp at 0. Okay, but again, you know it's not differentiable because the tangent is vertical. Okay, tangent is vertical, so option is x mod x. Okay, and that also tells you something. Okay, what does it tell you? Although in f into g, g may not be differentiable, or even if g is not differentiable, f into g may be differentiable. Got it? That is something that we can learn from this problem, that it need not always be true that for the product to be differentiable, the individual functions should be differentiable. We have seen that it doesn't necessarily it's not necessarily true that both functions should be differentiable for the product to be differentiable. Got it? Any doubt in sixth? No doubt? ठीक. Okay, this question is going to take us a long time, so I will skip it for time being. Yeah, okay, let's do this one. Okay, fifth, yeah, this was sixth, so let us go to seventh one. I will do this in our next lecture, this question. Let us go for this one. Okay, seventh one. This is from 2018. Okay, this is from 2018. Let f and g from R to R be such that f of x is equal to x raised to k into g of x, where k is a positive integer. That means k is a natural number. Suppose g is continuous at x equal to 0, then option A, f is continuous at 0 but not differentiable at 0. F is differentiable at 0. Third, f dash of 0 is 0 for every positive integer k. F dash of 0 is g of 0 if k is 1, and f dash of 0 is 0 if k is greater than or equal to 2. Okay, this is also a multiple select question, and we know that g is continuous but not differentiable. Okay, and well, just in the previous question we have seen that for the product to be differentiable, it's not necessary that, well, one of the two, both of them should be differentiable, right? Okay, so let us go for f of x, x raised to k into g of x. Okay, now what do we want? We want to check whether it is continuous at 0. K belongs to n. Is it continuous at 0? Yes, it is, because f of 0 is 0 raised to k into g of 0, and limit of f as x tends to 0 is f of 0, right? And x raised to k and g of x, well, again, if two functions are continuous, then the product must be continuous, right? So continuity is resolved. It's continuous. Okay, you can also write it here. Also can be proved using algebra of continuous functions. Okay, that if product of two functions is given and both individual functions are continuous, then the product must be continuous. Okay, so continuous part is there, but we haven't yet commented anything on the differentiability, so let's find out. Okay, how to find it out? let's use the first principle. Okay, limit as h tends to 0, f of 0 plus h minus f of 0 upon h. Okay, f of h is what we need. So at h it would be h raised to k into g of h minus f of 0. Yeah, f of 0 is 0, right? F of 0 is 0. Why is f of 0 0? Because k is a positive integer. Okay, k is a positive integer, so f of 0 is 0. I can write it here upon h. Okay, so what have we got there? What have we got there? Limit h tends to 0, h raised to k minus 1 into g of h. Okay, now look, I can write it as limit as h tends to 0, h raised to k minus 1 into limit as h tends to 0, g of h. Okay, now because g of h is continuous, g of x is continuous, as h tends to 0, this should tend to g of 0. Okay, this should tend to g of 0. But what about this? What about this? Okay, now here we consider two cases. If k is greater than 1, then this is equal to 0, like 0 squared, 0 raised to 1, 0 raised to 2, 0 raised to 3, they are all zeros. Okay, so that is 0. But what about k equal to 1? If k equals 1, then what will we get? Limit h tends to 0. Okay, well, we'll get something like 0 raised to 0 or h raised to 0, right? And h raised to 0 is how much? That's 1. No matter how close you go to that, h raised to 0 will always be 1. But 1 into g of 0. Okay, so in either of the cases derivative exists. And hence it is differentiable. Hence it is differentiable at x equal to 0. So option B is correct. Okay, now can option C be right? Let's think about it. F dash of 0 is 0 for every positive integer k. No, it will be equal to 0 for k greater than 1, but not k equal to 1. Every positive, so it would be true for every positive integer greater than 1. Okay, let's come to D. F dash of 0 is equal to g of 0 if k is equal to 1. That's true. And f dash of 0 is 0 if k is greater than or equal to 2. That's true. Why? Again, we have to split that. Okay, we have got it as k minus 1 because of the cancellation of 1 power of h in the numerator by this first principle definition of derivative. And therefore, when k is greater than 1, then we'll get 0. 0 into g of 0 is 0. But if k is equal to 1, then that limit is equal to 1. And therefore, f dash of 0, okay, let me write it in blue color. And therefore, f dash of 0 is g of 0. So when k equals 1, the derivative is g of 0. But when k is greater than 1, then that is 0. But more importantly, f dash of 0 exists. So which option is true? B is true and D is true, but not C. And A is also not right because it is differential. Have you understood this? Look, in such problems, when the first principle is to be used for finding the derivatives, in most of the cases the value where you want to find the derivative will be 0, so that it becomes easier to solve the problem. Okay? So question 7 is done. I will stop here for today. Yeah, wait. I'll give you this as homework. Okay? This 8th question I will give you as homework. It's very simple. You find out and yeah, this is also a multiple select question. from 2019. You take it, it's a very simple one. You just need to draw the graphs of these functions and tell me the answer in our next meeting. Okay, so we have successfully maintained the average of 8 MCQs per lecture, and in the next lecture, which we do tomorrow, we shall be continuing with derivatives MCQs. Okay, see you tomorrow same time.
Thank you, sir.
Welcome.